You know, when you type a prompt into like a massive generative AI, it's really tempting to think of the model as this pristine mathematical engine.
Right. Yeah. People definitely assume that.
Yeah, you just feed the data in, and these complex, perfectly logical calculations take place, and out pops a beautifully constructed response. I mean, we kind of imagine the internal workings are as clean as the physical microchips they're running on.
That assumption of geometric perfection is incredibly common, even among the people who actually build these systems. We instinctively just want to believe the underlying math is elegant.
But if you talk to the engineers who are actually looking under the hood of these multi-billion parameter models, you start hearing a very, very different story.
Oh, absolutely.
For years, researchers have been spotting these weird, messy glitches deep inside the networks, like pathologies, right? Little structural breakdowns where the AI just seems to be mismanaging its own data.
Right. Doing things that make, frankly, zero logical sense to the people who originally programmed it.
Exactly. And traditionally, the field has just treated those anomalies like isolated bugs.
Yeah, if a model gets, arbitrarily fixated on the wrong word,
Hmm.
researchers try to patch that specific behavior. Or if the data gets distorted in a deeper layer, they treat that as a totally separate issue.
But today, we are doing a deep dive into a state-of-the-art research paper that just completely flips that whole narrative on its head.
It really does. It's fascinating.
The paper argues that everyone has been looking at these glitches all wrong. They aren't isolated bugs at all. They're actually symptoms of one inescapable universal law that governs how AI processes information.
Which is a massive claim.
Right. So the paper is titled All Roads Lead to Collapse, and our mission today is to use it to unpack the foundational building blocks of generative AI. So, okay, let's unpack this.
Sounds good.
Before we get to the root cause of this universal AI behavior, we really need to understand the symptoms. Like, what exactly are these glitches researchers keep finding?
Well, there are three main phenomena that have historically been studied in complete isolation from one another. And we mostly see these within trained transformers.
Which is the architecture powering models like GPT, right?
Exactly.
Yeah.
So the first symptom is known as attention sinks.
Okay, to ground this for a second, attention is basically the mechanism the model uses to decide which parts of your prompt are important, right?
Yeah.
Like, if I type the cat sat on the mat, the AI uses its attention mechanism to connect the words cat and sat.
That is the ultimate goal of attention, yeah. But what researchers actually observed is that a massive, disproportionate share of the AI's attention gets absorbed by just a few tokens.
Really? Like which ones?
Often the very first token in a sequence, like the word the model essentially just fixates on it, pouring its computational focus into a word that carries almost no actual semantic meaning.
Oh, wow.
It basically operates like a sinkhole for the model's attention.
So the AI just gets stuck staring at the first word like it holds the secrets of the universe or something?
Pretty much, yeah.
Okay, so that's symptom one. What is the second symptom?
The second is called representation collapse. So to understand this one, you have to kind of picture how data physically moves through an AI.
Okay.
As information passes deeper into the layers of the model, it is stored in what we call hidden representations. You can think of this as the AI's internal scratch pad.
Right, makes sense.
Ideally, that data should live in a rich, high-dimensional space, so the AI can distinguish highly complex concepts. But instead, as the data moves deeper, those hidden representations just lose their dimensionality.
They just lose it.
Yeah, they drift and squish into a low-rank, shared subspace.
Let me make sure I'm visualizing this correctly. It's kind of like the AI starts out holding a fully rendered, highly detailed 3D object.
Right.
But by the time it gets to the back of its brain, it has forcefully flattened that object onto a 2D piece of paper and just lost a ton of detail in the process.
That is a highly accurate way to visualize it, yeah. The complexity just collapses.
Wow.
And that brings us to the third symptom, which is norm stratification.
Norm stratification. Okay, break that down for me.
So in the mechanics of attention, the AI uses a system of keys and queries to search for and route data. You can think of a query as like the search term you type into Google.
Okay.
And the key is the label on the web page telling you what the site is actually about.
That makes perfect sense. The AI is constantly matching queries to keys to figure out what information to pull next.
Exactly. And mathematically, you would expect the physical size or the norm of these keys to stay relatively uniform, so they can be easily compared to one another.
All right, apples to apples.
But instead, they spread out wildly. The sizes stratify. The AI starts massively inflating the mathematical size of some keys while dramatically shrinking others.
Okay, so let me pull this together. It's like going to the doctor for a cough, a fever, and fatigue,
Right.
and having 3 different specialists try to treat them as 3 completely separate diseases.
Exactly. Yeah.
But this paper is the doctor who walks into the room, looks at your chart, and says, no, you just have the flu, like it's all the exact same thing.
The paper makes exactly that argument. These 3 strange behaviors, the hyperfixation of attention sinks, the flattening of representation collapse, and the wild sizing of norm stratification. They're all 3 faces of one underlying mechanism.
Okay, so if these are all just symptoms of the exact same flu, what is the underlying virus? Like, what is actually causing the AI to behave this way?
The virus is a mathematical blind spot.
A blind spot.
Yeah, and it is hidden deep inside the very equation that makes modern AI work, which is softmax attention.
Softmax attention. Okay, so this is the core router we mentioned earlier, the mechanism matching the query to the key.
Yes, softmax attention acts as a distance-based router using what we call Boltzmann-weighted aggregation. It essentially
It's like
calculates...
Boltzmann-weighted aggregation.
Yeah.
In plain English, does that just mean it's scoring things based on how physically close they are to each other, kind of like creating a heat map of relevance?
That is a great translation, actually.
Yeah.
It looks at the mathematical distance between the query and the keys to determine which information is closest or most relevant.
Okay, got it.
But here is the critical discovery the researchers made through a mathematical reframing identity. The scoring equation the AI uses drops a very specific term.
What term?
It drops the magnitude, or the physical size, of the key itself. It's represented mathematically as the negative squared norm of the key.
Wait, it just completely ignores the size of the key.
It drops the term entirely. And what's fascinating here is that because this specific term is omitted, the AI's routing metric is rendered completely blind to the magnitude of the data.
That sounds like a pretty big flaw.
It is. The math essentially assumes that all keys are perfectly uniform in size, living on a perfectly smooth, flat, hyperspherical geometry.
But based on what you said about norm stratification a minute ago, they
Yeah.
definitely aren't uniform, right? I mean, the AI is wildly inflating and shrinking them.
They absolutely are not uniform. And the researchers measured this extensively. They looked at 9 different pre-trained transformers, including the GPT-2 family and the Pythia family.
Yeah.
And they tested them using a data set called Wikitext 103, which is just a massive collection of Wikipedia articles often used as a benchmark.
Right, to test how well the models understand language.
Exactly. And in every single layer of every single model they tested, the assumption that key norms are uniform was fundamentally violated.
Wow.
The underlying metric is blind to size, but the actual data the AI is trying to process is highly variable.
Okay, let me push back on this for a second, though.
Sure.
If the AI's core routing math is fundamentally blind to the size of the data it's sorting, wouldn't the model just fail? I mean,
Right.
if the engine is built on a broken equation, why does the AI go through this incredibly complex gymnastics routine of collapsing its data and creating attention sinks just to make the math work? Like, why not just crash?
Because the AI is driven by one overriding mandate during its training, which is to minimize its loss function.
Right.
It has to get better at predicting the next word no matter what. It needs to recognize the importance of certain data to make those predictions. But because the flat, norm-blind metric it was programmed with cannot see magnitude, the model is forced to find a workaround to pass the information it needs to survive the training process.
So it literally hacks its own geometry.
That's exactly it. To compensate for the blind spot, the AI forcefully squishes the representations into that low-dimensional space we talked about. That's the representation collapse.
Right.
It focuses all its routing power onto a few points, so they are impossible for the math to miss. Those are the attention sinks.
Yeah.
And it artificially inflates the keys it desperately wants to be noticed, which is the norm stratification.
Everything is connected.
Exactly. And the paper proved this happens early in the network, usually between 9% and 25% of the way into the model's depth. And once it happens,
Yeah.
it just stays locked in.
That is incredible. It realizes the mathematical tool it was given is broken, so it takes the raw materials, the data itself, and twists them to fit the broken tool just so it can keep learning.
Yeah.
But if this blindness is truly a universal property of the math, and not just a weird quirk of transformers like GPT-2, we would expect to see this happening in completely different AI architectures.
We would, yeah.
As long as they use the same routing logic, they should suffer from the same collapse.
And that was the exact next phase of the researchers' experiment. They wanted to test this theory on 4 non-standard models.
Okay.
These are architectures that don't use the standard token attention we see in the GPT models, but they still rely on some form of content-based routing.
So if we are moving away from standard text-based models, what kind of architectures are we talking about here?
Well, they started with graph attention networks, or gate
Yeah.
keys.
Okay.
Instead of routing over words in a sentence, these route over nodes in a network. Think of mapping relationships, like predicting connections on a social media platform or analyzing molecular structures.
Got it.
Now, graph networks have their own known issue called oversmoothing, where data naturally washes out and becomes generic over time.
Right.
So to ensure they were looking at the collapse caused by the math and not just generic oversmoothing, they tested the GAT against a basic non-learning control model called a GCN.
So they basically had a control group for the AI.
Yes,
Did the learning model collapse more than the control?
significantly more. The excess collapse in the GAT was specifically caused by the learned attention mechanism. It proved the geometry was warping because of the routing, not just the nature of graph data.
Okay, so it happens when mapping relationships on graphs. But what about models that process information over time?
For that, they tested Mamba.
Ah, Mamba.
Yeah, Mamba is a highly popular selective state-space model. It processes sequences linearly, updating a hidden state as it goes, which makes it very efficient.
Okay, here's where it gets really interesting for me, because if I understand Mamba correctly, it doesn't even have traditional query key attention.
Right, it doesn't.
It works completely differently than a transformer. So how did researchers prove this concentration wasn't just a total coincidence in Mamba?
Well, Mamba uses a selective scan that unrolls over time, rather than looking at everything all at once like a transformer.
Right.
The researchers actually had to dig in and reconstruct the hidden weights of Mamba's internal operators
Yeah.
just to see what was happening geometrically.
Oh, wow. And what did they find?
When they did that, they found the exact same concentration signature. It happens later in Mamba, usually on setting around 56 to 81% of the model's depth, but the collapse is undeniably there.
But finding the same signature is one thing, right? How did they prove the routing math actually caused it in a completely different architecture?
They performed what's called a causal ablation.
Wait, causal ablation? That sounds like they went in and surgically turned off the specific part of the model they suspected was causing the issue?
That's pretty much it.
Like knocking out a suspect gene just to see if the symptom disappears?
That is exactly what it is. In Mamba, the concentration of data is controlled by an input-dependent gate, which they call the selectivity mechanism. The researchers went in and froze that gate to its average value, completely disabling its ability to dynamically select information.
And what happened?
The moment they did that, the concentration completely flattened, the collapse just vanished.
Oh.
This causally proved that the routing mechanism itself is what creates the collapse, regardless of the architecture housing it.
So it's not the architecture at all. It's the sheer act of routing information using this math.
Exactly.
You mentioned it happened much later in Mamba than in the Transformers. If all these models face this gravitational pull toward collapse, why do some fall into it immediately in the early layers, while others seem to resist it until much deeper in the network?
That brings us to a fascinating concept the paper calls the positional break.
The positional break. Okay.
Having established that the collapse mechanism is invariant, meaning the math dictates it always happens, eventually we have to look at what is contingent, or what changes from model to model.
Right.
The researchers explore this using a third architecture called RWKV, which is a recurrent mixer that routes information over time.
So RWKV mixes past information it has already seen with the current information it is processing.
It does, yeah, and it has a very specific parameter for time decay. This parameter dictates how much of the past the model remembers or carries forward into its current calculations.
Okay.
The researchers initially assumed, as many in the field did, that giving an AI a larger memory capacity would distribute the routing pressure and actually delay the collapse.
Yeah, that makes logical sense. If you have a vast memory, you don't have to compress everything into one tiny spot immediately. You can just spread the information out.
Right, but this raises an important question. What if our intuition about memory in artificial intelligence is completely backward?
What do you mean?
When the researchers turned the decay heavily up, meaning the model quickly forgot the past and only focused on the present, the concentration flattened entirely. The collapse dropped to a tiny 0.015 in every single layer.
Wait, so forcing the AI to experience extreme forgetting actually stopped the collapse?
It did. But when they removed the decay entirely, giving the model full carry or perfect long-term memory, The collapse happened incredibly early. It hit the onset threshold at just 17% of the model's depth.
Wait, really? So giving the AI more memory doesn't delay the collapse at all?
No,
Memory actually creates the attractor that pulls the data into a collapse.
exactly. The time decay simply acts as a positional brake. It's a localized force that constantly pulls the AI's attention back to recent tokens.
Okay, I see.
And this fights against the underlying metric's natural urge to collapse all the data into a single content-based hub. Transformers have very weak positional brakes. Recurrent models have strong ones, which is why they collapse later. But eventually, the mathematical gravity wins out.
Okay, let me see if I can picture this. It's like putting a parachute on a falling object.
Okay.
The parachute is the AI's short-term memory. It creates drag by forcing the model to focus on recent words, which slows down the descent. But the underlying math is still gravity. The parachute just changes the speed of the fall, you know? It doesn't turn off gravity. You are still eventually hitting the ground.
That's a perfect analogy for the positional brake.
Hmm?
And to truly isolate this gravity, they looked at a fourth architecture called attention residuals, or ATNRS.
Okay, what does that one do?
This one routes information over depth, meaning the actual sublayers of the model, rather than over tokens in a sequence or nodes in a graph.
Wow.
And critically, ATNRS uses normalized keys.
Wait, normalized keys, meaning the math forces all the keys to be the exact same size.
Yes.
So norm stratification, that spreading out and inflating of key sizes we talked about in the beginning, is completely disabled by design.
By design, yeah. The models cannot stratify the norms.
So if it can't stratify the norms, does that mean they actually cured the collapse in this model?
Not even close.
Really?
It absolutely concentrates still. It creates massive hubs on the current block it is processing and on the original token embeddings, what the researchers call source zero.
Wow. So norm stratification isn't the cause of the illness at all. It's just one of the immune system responses.
Exactly.
If you block that response by forcing all the keys to be the same size, the AI just finds another way to collapse the data to deal with the blind spot. It is just relentlessly adaptive.
The concentration is a fundamental property of the content direction, which normalization just doesn't touch.
Mm.
The blind spot remains, so the collapse remains.
Okay, we have dug deep into some highly abstract geometric theory here today.
You definitely have.
And if you are listening to this, whether you're building these massive AI models, integrating them into your business, or just trying to wrap your head around how this technology actually functions, you might be wondering why this abstract math matters to you.
Right.
Like, why does knowing about this mathematical blind spot and this inevitable collapse actually change anything?
It matters fundamentally because it explains why the tools and hacks the industry currently uses to build and run AI actually work.
Give me an example.
Well, for example, the Pythia models we mentioned earlier use something called ropey rotary position embedding. It's an incredibly popular way to inject positional information into a model.
Okay.
And this paper shows that rope-E works by spreading out the angular geometry of the data.
Wait, spreading out the angular geometry? How does that actually work mechanically?
Imagine you have all your data points clustered together on a flat map.
Right.
Rope-E essentially acts like taking those points and placing them on a spinning globe. It physically rotates the vectors representing the data, forcing them to remain distinct from one another based on their position.
Oh, I see.
It acts as a positional brake that violently resists the collapse. Now, Rope doesn't touch the key norms, so it doesn't fix the underlying blindness of the equation, but it artificially diffuses the geometry just enough to keep the model functional.
So Rope-E isn't some elegant mathematical cure. It's literally just a coping mechanism we accidentally discovered that happens to perfectly counter the AI's urge to collapse.
Exactly. And if we connect this to the bigger picture, the most profound implication of this paper is what it says about fine-tuning.
Okay.
There is a hugely popular technique in the AI world right now called LoRA, or low-rank adaptation.
Right. LoRA is everywhere. Training a billion-parameter model from scratch takes massive data centers and millions of dollars.
Yeah, it's hugely expensive.
So if you don't have that kind of budget, you use LoRA to cheaply adapt an existing open-source model to your specific needs.
Right.
But adjusting billions of parameters should require massive computational power. LoRA gets around this by only making low-rank or low-dimensional updates to the model's weights.
And researchers have always marveled at why LoRA works so incredibly well. Like, why is it that you only need a tiny, low-dimensional update to drastically change the complex behavior of a billion-parameter model?
And this paper answers that.
This paper gives us the definitive answer.
Yeah.
LoRa works so well because the AI has already pressed all of its usable geometry into a low-dimensional collapsed subspace during its initial training.
Because it had to. It literally had to collapse its own brain to survive the norm-blind metric in the softmax equation.
Yes.
So, what does this all mean for you? It means the efficient hacks we use to train AI cheaply aren't just lucky tricks. They work because they align perfectly with how the AI has forcefully organized its own representations.
We've been throwing low-rank adapters at these models for years, marveling at our own cleverness, not realizing the model was already sitting in a low-rank posture waiting for us.
Wow.
The AI is essentially a vastly compressed funnel of information driven into that shape by its own routing metric.
Ooh.
You're just taking advantage of the shape it was already forced to take.
That is wild. Well, thank you so much for joining us on this incredibly complex journey into the geometry of AI mind.
Well, thanks for having me.
We've taken apart the math, we've looked at the underlying symptoms from attention sinks to norm stratification, and we've seen how this universal routing law applies across completely different architectures, whether they process text, map graphs, or unroll over time. But before we go, I want to leave you with one final thought to mull over.
The paper clearly frames this norm-blind metric as an inadequacy, like a mathematical flaw that the AI has to desperately compensate for by twisting its geometry into a low-dimensional subspace.
But what if we zoom out? If this exact same compensation signature appears across billions of parameters, across entirely different architectures, routing over time, routing over tokens, routing over depth, I mean, maybe this collapse isn't a bug at all. Think back to our medical analogy at the start. We thought the AI was sick with the flu because it was behaving strangely. But maybe, in the universe of information processing, collapsing billions of data points down to their most concentrated, biased essence isn't a pathology. What if filtering out the noise and squishing the world down into a simplified, accessible format is the fundamental definition of what it means to learn? If we actually go in and fix the math and remove the blind spot, do we cure the AI or do we break its ability to think?